Hi folks, in this video we're going to have a look at an example of charging a capacitor and then connecting that capacitor across a second capacitor in parallel and the calculations involved with that. In our question we have a 2.0 millifarad capacitor which is charged by a 100 volt supply, and we have a 1.0 millifarad capacitor which is charged by a 200 volt supply. Part A of the question is asking to calculate the energy that is stored in each capacitor. So we have a couple of different equations that we can use in order to determine the energy that's stored within a capacitor. So the work done, or the energy that is stored in a capacitor, is equal to a half multiplied by the charge multiplied by the voltage. That can also be written as a half multiplied by Q squared over V, or we could say that it's equal to a half multiplied by C times V squared. So given the information that we have in the question, the equation that suits us best is this last one here, a half CV squared. So to work out the energy stored in each capacitor, we will first look at the 2 millifarad capacitor. So I'm just going to put a 2 subscript on there. That is equal to a half multiplied by C multiplied by V squared. So we have a half multiplied by the capacitance, which is 2.0 by 10 to the minus 3 farads, multiplied by V squared, which is 100. And if we pop that into a calculator, we get an answer of 10 joules. Now, if we look at the energy across the 1 microfarad capacitor, the energy stored, or the work done, is equal to a half CV squared. So we have a half multiplied by 1 by 10 to the minus 3, multiplied by the voltage in this case, which was 200, and that is squared. And when we pop that into a calculator, we get a value of 20 joules. So the capacitors are then connected in parallel with each other, with like charges connected together. So part B is asking, calculate the capacitance of the combination. So we need to use the appropriate equation here for capacitors that are connected in parallel to each other. And that equation is that the total capacitance is equal to the sum of the individual capacitors, which in this case is the 2 millifarad capacitor plus the 1 millifarad capacitor. So in total, we have a capacitance of 3 millifarads. Part C. Calculate the total charge stored in the combined system of capacitors. So in order to do this, we're going to need to use our calculation to figure out how much charge was put onto each separate capacitor. So let's look first of all at the 2 millifarad capacitor. Now our equation for capacitance that links it to charge is C is equal to Q over V, because capacitance is the amount of charge stored per volt. So if we want to work out the charge, we can rearrange that equation to give us the capacitance times the voltage. So if we look first of all then at the 2 millifarad capacitor, then the charge stored on that capacitor will be 2 by 10 to the minus 3 multiplied by the voltage across that capacitor when it was charged, which was 100 volts, which will give us an answer of 0.2 coulombs. If we now work out the charge across the 1 millifarad capacitor, so we're using the same equation here, but we have 1 multiplied by 10 to the minus 3 multiplied by 200. And that will give us an answer of 0.2 coulombs. So the total charge that we have in this system is the sum of the charges across each capacitor. So 0.2 plus 0.2, which will give us a total of 0.4 coulombs of charge. Now that is the total amount of charge that's in the combination, but each capacitor will not have 0.2 coulombs of charge once they've been connected together. That charge will redistribute itself until the potential difference across each capacitor is the same. And that's what part D of the question is asking us to figure out. They're asking us to calculate the new voltage across the combined system of capacitors. Remember that whenever the 2 millifarad capacitor was charged initially, it had a voltage of 100 volts, and the 1 millifarad had a voltage of 200 volts. So when they're connected together in parallel, there will be a movement of charge so that they both have the same voltage across. And that charge will move from the higher potential to the lower potential. So it will move from the 1 millifarad capacitor to the 2 millifarad capacitor. In order to find the new voltage, we are again starting off now with the equation C is equal to Q over V. But in this instance, we're going to use the total capacitance of the system and the total charge of the system, and that will give us the overall voltage across this network now. So if we rearrange that equation there, the total voltage is the total charge, or equal to the total charge divided by the total capacitance. So we previously worked out that the total charge was 0.4 coulombs divided by the total capacitance, which was 3 millifarads, so 3 by 10 to the minus 3. And when we plug that into the calculator, we get 133 volts. For part E, calculate the total energy that's now stored in the combined system of capacitors. So the energy that's stored in a capacitor is equal to, again, we have a number of equations that we can choose. We could choose a half QV, and if we put in the numbers there where we have a half multiplied by the charge, the total charge that's in that combination, which we worked out earlier, which is 0.4, multiplied by the voltage across the system, which we've just calculated at 133, and in the calculator then that would give us an answer of 26.6 joules. So that value of energy that's stored in that system, the 26.6 joules, is less than the energy across the two capacitors when they were separate, because initially we worked out that the 2 microfarad capacitor had 10 joules of energy and the 1 microfarad had 20 joules of energy. That was a total of 30. But now when we've connected them together, we've only got 26.6 joules. And that's part F of this question. It's asking you for you to account fully for the difference in those answers. So as we've mentioned already, charge will have moved from one capacitor to the other. It will have moved from the 1 millifarad capacitor to the 2 millifarad capacitor, because it's going from a high potential to a low potential, from the 200 volts to the 100 volts. And it does that until the voltage across each capacitor is the same. So while those charges are moving, then there is resistance in the wires, albeit low, but there is resistance there, and that energy is being lost as heat as the charges are moving through the wire. So the total charge across the capacitors is conserved before and after we connect them together, but the total energy across the capacitors is not conserved. And that's because some of that energy is lost as heat in the connecting wires whenever the charges are moving from one capacitor to the other. So that's it, and hopefully you found some of that useful.